So the second example, I have now two fixed supports. Let's go with the 8 steps, one by one again. So what will be the first step? I have to calculate the degree of indeterminacy, which is n minus e, number of redundants minus number of equations. How many redundants now I have? Take care in this example for how to calculate the degree of indeterminacy. It's not as easy as the last example. There is like a small trick, so concentrate when calculating the degree of indeterminacy for this specific example. Okay? What are the number of redundants? 3 here and 3 here, so total of 6. What about the number of equations? The equations, the equilibrium equations I have, the sigma x, sigma y, sigma moment, so there are only 3 equations. So the degree will be 3, right? No, not right. There is a small trick here. What's the trick? When you find more than one horizontal reaction, if there is more than one horizontal reaction, there is a trick here. The last example, was there more than one horizontal reaction? No, it was fixed and roller. So it was only one horizontal reaction, right? But here is the trick. Here there are more than one horizontal reaction. Let's see the requirements. As I told you from the last example, you will not be required to draw the normal force diagram, right? So you will not need the horizontal reactions. The horizontal reactions, you need them only when you are drawing the normal force diagram, right? Here, you only need the shear force diagram and the bending moment diagram, so you don't need the horizontal reaction, right? So when you find more than one horizontal reaction, just remove them from the reaction. So the 6 will be 4. But at the same time, the equations will not be 3. You remove the horizontal reactions from the redundants, so remove the equation of sigma x equals 0 from the equation. So the 3 equations will be only 2. So the right degree here is 2, not 3. So this will be the first step, how to calculate the degree of indeterminacy. So what will be the next step? Main system. The last example, the degree was 1. So I decided to remove only one reaction. Now the degree is 2, twice. Statically indeterminate. So I have to think of removing 2 redundancies. Okay? What will be the 2 redundancies? It's clear here. So the fixed supports at A and B, I will convert them to hinged support. Okay? So I remove the moment at A and the moment at B. Right? I have to decide here in the second step the naming of each redundant. It's very important, the naming. Which one of them will be called X1 and which one will be X2, because it will depend on the naming here, the whole solution. Here you are free to decide. Either MA is X1 or MB is X1. It's totally up to you, okay? But once you decided here, take care from the naming in case node and case 1 and case 2. Yes, here in the twice, there will be case 2. In the last example, there were only 2 cases, case node and case 1. Case for each redundant and case for the loads. So case node for the loads only, and each redundant will have an additional case. Okay? So I have here case node for the loads, and I will be having 2 additional cases for each redundant. Okay? So let's decide here the x1 will be MA, as you like. I decided to choose this for MA, and the x2 will be MB. Okay? So what will be the main system? It will look like this. It will be a simple beam. Okay? Not hinged. When you remove the fixed, the moment that the fixed support, it turns to hinged support, right? But as I told you before, in structure 2, we are not concentrating on the normal force back. So it will not differ the roller support with the hinge support. It will be the same meaning for me. So 2 hinge support, I even don't put the wheels of the roller or the dashes for the hinge support. I leave them like this. So 2 supports from this side, roller or hinged. It's not my matter here in structure 2. Okay? So this will be the main system, which I call case node. And I have only one node at point C. Okay? What will be the next step? Okay, you have determinate structure, case node. You have to draw bending moment, which is called M node. In order to draw bending moment diagram, I have to first calculate the reaction. What will be the reactions here? Moments. Take moments here. So 9 times 6 minus y times 9 equal 0. So this will be 6. So this will be 3. Now I can draw the bending moment diagram. The moments at the edges are equal to 0. I need to calculate the moment at C, either from the right or from the left. From the right, it's 6 times 3, or the same from the left, 3 times 6, which is 18. And no distributed loads, so no parabolas. It's only linear straight line like this. This is called M node. And this is 18. I will put it on a conjugate beam, like we did in the last example. What will be the conjugate beam of the simple beam? Remember the table, the last example? For the simple beam, it remains the same in the conjugate beam. So here, the conjugate beam will be the same as the main beam. So now, let's remember the 2 main positions that I have to split the areas of the bending moments. I have 2 main points, 2 main positions. What is the first position? The point that I am going to calculate a displacement at, which have the same meaning that the redundant I remove. So I am removing redundants here at A and B. So I am going to calculate a displacement at A and a displacement at B. Okay, but A and B are on the edge, so no splitting needed here, right? What is the second main position that I have to split the bending moment before I calculate the areas? The difference in inertia. Do I have difference in inertia here? Yes, I have the difference in inertia at point C, which is already splitted at point C because I already calculated the moment here. So I don't need extra splitting. So how many areas do I have now? I have only 2 areas for the 2 triangles. The first triangle from A to C, it will be downwards because it is down the datum. And the other triangle, it will be on the 1/3 and the 2/3, also downwards because the moment is down the datum. Okay? How much is the first force? It's the area, half, times the base is 6 meters, height is 18. Only the area? No, it's the area divided by the inertia factor here is 3. which is 18. What about the second force? It's half. Base is 3. Height is 18. Divided by the inertia factor, which is 1. So here will be 27. 27, right? 27. Okay. What I'm going to calculate here, I'm going to calculate theta A and theta B. What is the main form, the general form? I calculate the displacement that is corresponding to the redundant I have moved. I removed a redundant at A, which is the moment, so I have to calculate the rotation at A. I removed another redundant at B, which was also a moment, so I have to calculate the rotation at B. Okay? What is the rotation in the deflection? Rotation is the shear at A from the conjugate divided by EI, and the same for B, shear at B divided by EI. So first I have to calculate the reaction. Why in this case I have to calculate the reaction of the conjugate beam, and in the last case I didn't calculate the reaction? The last case, it was fixed free, the main beam. So the conjugate was free fixed, and I was going to calculate a displacement here at this point, so I can calculate the moment either from the left or from the right. So I decided to calculate from where? From the left. So no need to calculate the reaction. You are wasting the time. But here, if you are going to calculate either way, right or left, you have a support here and you have a support there, so you have to calculate the reactions. How can I calculate the reactions? Take a moment. This is 18, this is 27. Take a moment here. So 18 times 2/3 of the 6, which is 4, so 18 times 4. And then 27 times 7, which is 6. And 1/3 of the 3, 1, minus y times 9 equals 0. What will be y? I think the value, I have it. Sigma y 18 and 27 is 45, so this will be 60. Okay? I now need to calculate theta at A, which is shear at A. What's the definition of shear? What is the shear at a point? It's a summation of the vertical forces either from the left of this force or of this point or from the right. The general form is not only the vertical force, it's the perpendicular force. But here, because I'm talking about the horizontal beam, so the shear will be perpendicular to the horizontal, which is vertical. So shear here is the summation of any vertical forces either from left of A or and B. You decided to name it 2, so here it will be called 2. So here it's theta 1 node and theta 2 node. What about the shear at B? Shear at B. So take a section right beside B. Either from the left 16 and 18 and 27, or from the right it will be only 29. It will be the same, right? So 29 from the right upwards, so it is negative 29 divided by BR. Now I finished case 1. Okay, what about case 1? Case 1, so it's related to MA. and case 2 will be related to MB. Okay? So case 1, the same main system, I will name it case 1, but without loads, no 9 tons. Only I will put a unit load instead of the redundant I removed. What was the number 1 redundant? It was MA. So now I will put a unit force at A. But this was a moment. The last time I was removing a roller support that was having a vertical reaction. So I put here a vertical load 1 ton. But here I am removing a moment. So I am putting here a moment 1 ton meter. So I made an assumption here that X1, that is MA, has a value of 1 ton meter. And then repeat everything again. How? Draw bending moment. It's easy to draw bending moment here. You don't need to calculate the reactions, right? It's just 2 nodes. So here the moment is 0, and here the moment is 1. The one you put. So it's a triangle. This is M1. Put it in the conjugate B, which will be the same. You need splitting? Yes, I need splitting because I have a difference in inertia here. So I have to split this triangle. I can't make it 1 triangle. So I have to split it, this triangle, and then trapezium on the left, which will be a rectangle and a triangle. So I need to know what is this value, right? Similarity, small triangle with the big triangle. So how much will this be? 1/3, yeah, it will be 1/3. Okay? So what's the value of this? This will be a triangle, half base times height. Half base is 3 meters, height is 1/3, divided by inertia factor, which is 1. So this will be, I think, 1, right? Half, third, 1/3 times 3, which is 1. Like this, half. Base is 3 meters, height is 1/3, divided by inertia factor, which is 1. It will be half. Okay? The rectangle here, 1/3 times base is 6, divided by the inertia factor, which is 3. I think this will be 2/3, right? The triangle, half the base is 6. The height is the difference between 1 and 1/3, which is 2/3, divided by inertia factor, which is 3. 2/3. Now I have to calculate the reaction, same I did in case no. How can I calculate the reaction? Take a moment here. So 2/3 times 2, 2/3 of the 6, and then 2/3 times 3, and then half times 6 and 1, which is 7, minus YB times 9 equals 0. So YB will be 0.76. Sigma YA will be 1.08. Okay? I need to calculate theta A and theta B. What are they called? I am now in case 1. So the second number will be 1. The first number is the redundant number. A is the redundant number 1. So it will be 1, 1. B is the redundant number 2. So it will be called 2, 1. What is the theta at A? It's the shear at A. Theta at B, the shear at B. They are ready. Shear at A is 1.08 divided by EI. I calculated the 1.08 from the left, and it's downward, so negative. Theta B, 0.76 divided by EI. I calculated it from the right and downwards, so it's positive. طيب احنا again, why I am calculating theta at A, theta at B in each case? I told you this before in the last example. In the beginning of the example, you should know what will be the helping equations you will use. The helping equations will be depending on the displacements, the deformations, right? Not the forces. So here you remove the redundants at A and at B, right? So what about the displacement at A and the displacement at B? This is a fixed support, so it can't move. The horizontal displacement equals 0, the vertical displacement equals 0, and the rotation equals 0, because it has 3 reactions, x and y and moment, right? And what about the displacement at B? All of them are 0 as well, because it's fixed. But I don't need the whole displacement. I have to think about the displacement that is corresponding to the redundant I removed. I removed moment, right? So I just need the rotation. So the rotation at A equals 0 and the rotation at B equals 0. I should know that these will be my helping equations that I will use in the condition at the end of the example, right? So that's why in each case I am preparing myself for the condition, right? So that's why in case note I am calculating theta at A, theta at B. Case 1, theta at A, theta at B. And case 2 as well now, theta at A and theta at B. Why? To be ready to solve the 2 equations in the last step, which is called the condition, which I know that it will be the theta at A equals 0, the theta at B equals 0. Okay? That's why I am calculating both of these rotations at each step. Okay? So what about case 2? Now, the same. The main system without any loads, just for the second redundant, which was MB. Now I will put a moment at B equals to 1 per meter. I will assume that the value of x2 is 1. I don't know the value yet. So I will assume that it's 1. Okay? And the same, I will draw bending moment diagram. I don't need the reaction. Here the moment is 1, here the moment is 0, this is M2. I will also put it on a conjugate beam. What will be the conjugate beam? It will remain the same, simple beam. Again, the same question. Can I make this triangle a whole triangle? No, I have here got difference in inertia, so I have to split these areas into 2 areas. How can I bring this similarity? Now it will be 2/3. Here I have got a triangle upwards because it's drawn above the data. Here I have got trapezium, which will I divide to a rectangle and a triangle. The value of this is half. Base is 6. Height is 2/3 divided by the inertia factor, which is 3. 2/3. The rectangle, base times height, 2/3 times 3 divided by 1, which is 2. This small triangle, half, base is 3, height is the difference between 1 and 2/3, which is 1/3, divided by inertia factor, which is 1, so this will be half. Right? Let's calculate the reactions. Take a moment here. 2/3 times 4, 2/3 of the 6. 2 times 7.5, 6 and 1.5. Half times 8, 6 and 2/3 of the 3, which is 2. And then y times 9 equals 0. Here I can get the reaction at B, which will be downward because all of them are upwards. It will be 2.41. And this will be 0.76. Okay? What do I need from this case? The same. Theta at A and theta at B. What are the names? I am here in case 2, so the second number will be 2. The first number is a redundant number. A is the first redundant, B is the second redundant. 1, 2, and 2, 2. What's the shear at A? 0.76. It's from the left and downwards, so negative 0.76 divided by EI. Shear at B, it's from the right downwards, so positive 2.41 divided by EI. As you can see, that the twice statically indeterminate examples are longer than the ones, because there's not only an extra case, no, there's also an extra calculation in each case. Okay? But I have a very good check. I can check my solution is right or not. What is the check? Theta 1, 2 and theta 2, 1 must be equal. Theta 1, 2, even you are calculating that, it's not only theta. The displacement that is called 1, 2 and the displacement that is called 2, 1, they have to be equal. I don't mean the sign, I mean the value, okay? So here, 2, 1 is 0.76. 1, 2 is also 0.76. So this is a very good check to make sure that I am on the right way. Okay? What will be the condition? The last step. I have 2 redundants, so I'm supposed to have 2 equations. What are the 2 equations? The first one, theta at A equals 0. The second one, theta at B equals 0. Right? Okay, what's the theta at A? I have a lot of theta at A. Theta at A from case node, which is called theta 1 node. Theta at A from case 1, which is called theta 1, 1. And the last theta at A from case 2, which is called theta 1, 2. So, theta at A will be theta 1 node from case node. and this is a real value for the theta at A. Why it is a real value? Because case node, you consider only the loads. Did you take all the loads or you take some of them? No, you took all the loads. So theta 1 node is a real value. But what about theta 1, 1 from case 1? No, it's not a real value. Why? Because you made an assumption here that x1 equals 1 per meter. It's not equal to 1. So what's the value of x1? I don't know. The value of x1 is x1. So before I put theta 1, 1, I have to put x1 multiplied by x1 to be the real value for theta at A from case 1. What about theta 1, 2 from case 2? It's also was based on an assumption that x2 equals 1 per meter. The real value for x2 is not 1 per meter. What is the real value? I don't know. It's redundant. So I have to multiply the theta 1, 2 by x2. This will be the real value. All of this equal 0. This is equation number 1. What about theta at B equals 0? The same. So theta 2 node plus x1 theta 2 1 plus x2 theta 2 2 equals 0. This is equation number 2. What about the EI value? All of the thetas has EI, and the right hand side equals to 0. So you can remove the EI from the 3 terms here, the same as in equation number 2. So you have to solve in the calculator these two equations for the two redundants x1 and x2. x1 will be equal to 8.25, positive 8.25 ton meter, which is MA, and x2 will be equal to positive 9.43, which is MB. What does the positive mean? The positive mean that the direction I assumed is correct. What was the direction I assumed for MA, for x1? See, I assumed it's in this direction. The tail is upwards. So my assumption was correct. x2 also is positive. I also assume the tail of x2 is upward, so my assumption is correct. So what will be the last step now? I have to draw the shear force diagram and the bending moment diagram. So I know now that MA in this direction and equals to 8.25 and MB equals to 9.43 and in this direction. Now easily I can calculate YA and YB by the equilibrium equation sigma y at sigma moment, and you can now draw the shear force diagram and the bending